Hello guys, how you doing? Uh, One of the founding fathers of the United States, Benjamin Franklin, once said, "An investment in knowledge always pays the best interest." The reason why I told this saying is, anything and everything we do, we should get some sort of information, or we'll have to try and understand and improve our knowledge on that. So I hope this presentation would add as an added advantage or give some sort of knowledge to you as well as me. Uh, so let's begin with the presentation. The topic of the presentation is breakpoints and halting in distributed programs. Before um, beginning the presentation, I would like to introduce you myself. As you see the image over here, it's me. My name is Rakesh KB, studying MTech in Web Technologies, Department of Computer Science and Engineering, Pesit College, Bangalore. So let's see what's the agenda of the presentation. So this is a IEEE paper that I will be presenting before you. So the agenda would be pretty straightforward of what the main topics in the IEEE paper consists of. So I would be starting off with the abstract, which kind of gives you a high level a view of what the presentation is. Then we would I would be giving you a brief introduction of what we are going to talk, what are the algorithms that we will be discussing, and problems with one algorithm which another algorithm overcame, and the reason why we implemented that particular algorithm. That's all. And the topic itself tells breakpoints and halting in distributed programs, right? So the third concept would be distributed breakpoints. So we would see, we would try to understand where exactly we can actually halt the program basically, and then consistent halting. So the main agenda of this particular presentation or this particular IEEE paper is to make sure that the programmers are able to halt their particular program or halt their process at any point in time, at any specified line, whichever they are interested or whichever they like to halt, and then kind of go back and see if everything is correct, and if there are some bugs they can actually fix that bugs, that sort, and then resume the program from that particular breakpoint. And then so anything and everything has to have an advancement. So this technology or this particular IEEE paper also is going on some sort of advancement in that. So we would see what is the application to current research. There are some applications, and there are some applications that might be invented by other people who actually go through this paper and would feel that they can actually improve this particular concept. And then finally we'll conclude by giving a high level understanding of what exactly we studied, and the references is basically just to say you guys that these are the materials or articles that I have been browsing through to get a fair idea of what this paper presents, what this paper talks about. So without wasting much of your time, let's quickly start with the presentation. So the abstract is pretty simple. I won't say it's pretty simple. It's plain English basically. If you just read it once, it's actually easy to understand. So you see the word called as interactive debugging, right? I think most of the programmers are familiar with the word called as interactive debugging, but I would like to give a short or brief description of what interactive debugging is. So interactive debugging is basically a powerful way to find and fix bugs. So any programmer would love to have interactive debugging in his the IDE which he's working on. So that's pretty much it. So it's a powerful way to find and fix bugs, and also to try out new code. Basically, if you find some bugs, right, so you'll have to go and fix those bugs. So it's pretty much that's it, and it's all done real time. So The programmer writes a code, tries to execute it. He finds some bugs. He try to cut it into breakpoints and see if these lines are executing, particular lines are executing. So say suppose 10th line has some problem, right? So that would be the breakpoint. He would try to fix that particular problem and then resume his program. So it's all real time. It's all live basis. So let's see what the abstract tells about. So like I said, the basic requirement of interactive debugging is that the programmer should be able to halt a program at interesting points in its execution, right? So in this presentation we will see the definition of distributed breakpoints with an algorithm for implementing and detecting these breakpoints. The definition of distributed breakpoints is based on those events that can be detected in a distributed system. Events that can be partially ordered or detectable and form the basis of the breakpoint predicates, and an algorithm that can be used in distributed debugger to detect these breakpoints. So these are the things that we would be seeing. We would be seeing what distributed breakpoints are, and we would see what an event is, and we would see what the predicates are. And also the halting algorithm extends something called as Chandy and Lamport's algorithm. So we have a very famous algorithm called as Chandy and Lamport. So Chandy and Lamport are two people who invented this algorithms. So this algorithm is for recording global states and solves the problem of processes that are not fully connected or frequently communicating. So it's basically it's a very good algorithm which actually tries and understands, and it actually solves the problem where the processes are not frequently communicating, right? And the programmer needs to halt some part of the program so that he understands it in a better way, and then tries to make sure that everything is working and then proceed on. So that's pretty much it. So the abstract, it's plain English, it's good. Going on to the introduction part, right? Yeah, like I said, interactive debugging requires that the programmer be able to halt a program at interesting points in its execution. Now, halting consists of the mechanisms to stop the program's execution called breakpoints, right? So, like I said, say suppose there are 15, there's a program which has like, say let's take a simple example, 15 lines of code, right? So if I feel that I'll have to see there's a very very critical logic at the 10th line. So if I feel that there's some sort of error in that particular logic, right, I'll have to go and break my program at that particular line, right? Then I'll see if the logic is working fine, and then I'll resume my program. So that particular point, that the 10th line, is called as a breakpoint. Now in this presentation we define a distributed breakpoints with an algorithm for implementing these breakpoints, and also present an algorithm for halting a distributed program in a consistent state. So we would see a breakpoint for distributed breakpoint or an algorithm for distributed breakpoints, as well as a algorithm for halting this distributed program, right? There are quite a few examples that actually would help us understand it in a better way. Say for example, when we say that say two people are coding, right? So we are just doing an interactive coding basically. So when I say to my colleague that the program should stop when procedure X is entered or when procedure Y is entered. So what do I mean by that? What I basically mean is to stop the program when any of these conditions becomes true. That's all, right? It's very simple. So when we say stop procedure X or stop procedure Y when either of the things is true, that's pretty simple, right? Also sometimes we might have an AND condition. So when I would say stop procedure X is entered, and also array of I element is equal to 10. So if both these conditions are true, the program would stop. That's it. Now so the author also tells that we have no single global notion of time in a distributed system, so we may not be able to determine whether one condition really occurred before another, right? So in this second example which I gave you, in that AND case, right, we may actually not be able to determine which condition really occurred before the other. So it's very difficult to know which one occurred first and which one next. So this means that we will have to tolerate breakpoints that occur independently on different machines. Likewise, we cannot determine whether events on different machines occur simultaneously. That's also a little difficult, right? Yeah. So that's how the introduction is. So we would see what distributed breakpoints are, what a halting algorithm is, and all these things. Let's move on to the next slide. Distributed breakpoints, right? So this slide pretty much talks about the definition of predicates for breakpoints in a distributed program. So the definition is based on detectable ordering of events. I would give a small introduction of what events is. I know everybody would be knowing, everybody are familiar with what an event is, but an event in this scenario is a little different, so I would be telling about what that is. So if you see the second point is types of breakpoints in distributed debugger, right? So in a sequential programming, the decision to halt the program is usually done by specifying predicates about the programmer's behavior and state. The satisfaction of these predicates correspond to interesting points in the execution of the program, which we call as breakpoints. I actually explained, I gave you that example, right? So like 15 lines of code and 10th line we have some problem, and then so halting a program at a particular line is called as a breakpoint. So the predicates are expressed in terms of events that correspond to a particular behavior or change in the state of the program. Now there are different types of predicates basically. So there are simple predicates, there are disjunctive predicates, there are conjunctive predicates, there are linked predicates. We would see we would have a slight brief, just a brief introduction of what these things are. These are all basic formulas that has been given in the article. Finding out what exactly this particular formula tells is actually out of the scope of this particular article. So it's an entirely different topic itself. So deriving to this particular expression, we'll have to find out that, but that's completely out of this particular presentation. So we would actually have a slight small introduction of what all these things are. So a predicate that is based entirely on execution behavior or state of a single process is called a simple predicate, right? So simple predicate is it's nothing but it's just based entirely on execution of a single process. Now we can also combine these simple predicates using the disjunctive operator. So I think we had the subject called discrete mathematics, right? So we were studying about something called as disjunction operator, conjunction operator. So disjunction operator is nothing but the union symbol, right? And conjunction is nothing but the intersection symbol. So that's pretty much about it. So we can combine the simple predicates using the disjunctive operator to make a disjunctive predicate. Likewise, we can combine simple predicates using conjunctive operator to make conjunctive predicates. So basically, using disjunctive operator, we can make disjunctive predicates by combining it with simple predicates, and simple predicates combined with conjunction operator makes conjunctive predicate. That's pretty much of these things. And let's see what the formula tells. So if you see the last point, the disjunctive predicates are specified by the expression using the disjunctive operator. Like I said it's the union operator, right? And it's combination of simple predicates, right? So one or more simple predicates form disjunctive predicate with the disjunctive operator. And the same is the case with conjunctive predicate. So it's only the symbol that's changed. If you see it's just the symbol that's been changed. So instead of union, we just have instead of union we have the intersection symbol in this particular conjunctive predicate. And there's also something called as linked predicate. So linked predicates uses a symbol. We used to use. I call it as tends to. So linked predicate is equal to it's a combination of disjunctive predicates basically, but there's a slight difference in the operator that they have used. Deriving this particular expression, I think it's not required over here. We'll understand what these things are. So let's take a small example, and let's just see. If you see here, there are two processes, right? Process 1 and process 2. Now, given two processes, process 1 and process 2, residing on different machines. Say this is residing on machine A and this is residing on machine B. Each process has its own virtual time axis, obviously, right? So this has its own time axis called as T1, and this has its own time axis called as T2, respectively. Now, a predicate SP1 is based on the state of process P1, and predicate SP2 is based on the state of process P2. We define a pair of virtual time points. So a pair of virtual time points is basically nothing but, if you see here, T11, T12, right? So a pair of virtual time points would be T11, T12. So let's take it as T1 and T2 to describe a time when SP1 is satisfied such that T1 belongs to the time axis T1. Now this would be written as SP1 brackets of T1, and it's obviously true. And the same is for SP2. Now, since T1 and T2 are virtual time axes, it's not always possible to order a given virtual time T1 on P1 and a given virtual time T2 on P2 according to Lamport. So we spoke about Chandy and Lamport, right? So Lamport says since T1 and T2 are virtual time axes, it's not always possible to order a given virtual time T1, small letter T1, on process P1, and on a given virtual time T2 on a process P2. But he says we can divide the process into two subsets named the ordered SEP, where there is an ordering between T1 and T2, and unordered SEP where there is no ordering. So it's nothing. So he is telling, T11 and T23 has some sort of ordering, and T12 and T22, there is some sort of delay over here, and there is no ordering. So basically these are ordered, and T12 and T22 are unordered. So that's pretty much what Lamport is saying. Let's see what the next slide is. So there's a implementation of link predicate detection. So basically there's an algorithm. So this is pretty much straightforward. It's it's just plain English that's given. I think it's easy to understand. It's just readable. So I'll just go through this algorithm. So there are basically two states, right? So two processes and two different rules for the processes. So say suppose there's a process P and there's a process Q. P is a process which is sending something, and Q is a process which is receiving something, right? So there's a sending rule for process P and there's a receiving rule for process Q. Now let's start with the first one, predicate marker sending rule for process A. What it does is send a predicate marker containing the link predicate on each channel C. Now what this channel C means is there are two processes, P and Q, right? So for these processes to communicate, there should be some sort of communication mechanism, right? So this mechanism is nothing but the channel, and we denote it as C. That's it. And for the receiving rule for process Q would be, if the same predicate marker has already been received, then why will Q receive the same thing, right? Then Q will just ignore it. That's it. Else, I think you are getting it, right? So if P is trying to send some predicate marker and Q already has it, and that's the reason Q is just ignoring it. Say if Q is not having it, what will Q do? If Q is not involved in the first incentive predicate of the link predicate, then do the predicate master sending rule. It does the predicate master sending rule again. So basically it would be sending the next predicate marker rule. So if Q has not even had that predicate marker, then there is a separate process which is this else part. So this tells separate the first disjunctive predicate from the link predicate carried by the predicate marker. In that formula we have, right? So basically they would be separating a disjunctive predicate and the link predicate, and then when the extracted disjunctive predicate is met, if the new LP, so there is a variable called new LP, if this is null, then initiate the halting algorithm. So we would see what halting algorithm is. Else send a new predicate marker containing the new LP as a new link predicate according to the predicate marker sending rule. It's plain English, right? I think it's a wonderful algorithm. It's really good. It's just once read and you can understand in a better way. Let's see what Chandy Lamport's algorithm says. So I think I have explained this pretty much, but still let's go through once. Chandy Lamport's algorithm. So a distributed program consists of finite number of processes and finite number of channels between the processes. That's always true, right? So 2 people talking are finite, 10 people talking are finite. There can't be in a particular scenario, right? So in a computing system, there are defined processes, right? There cannot be undefined processes, right? So all the processes are finite, as well as the communicating channels are also finite. Now the figure 3.1, we see this is the figure 3.1, shows an example where each process is represented by a circle and channels are represented by the directed edges. Processes in a distributed program communicate by sending and receiving messages. That's something that we have learned from our pre-university days, right? So they communicate using sending and receiving messages. Now channels are assumed to have infinite buffers. Obviously that's pretty much true, right? So a buffer size can be a large, small, depending upon the system that they're using. So basically the reason of having buffers is to be error free and to deliver the messages in the order that they are sent. Like I said to you before, right? So there's an event, there's a definition for the event that we are talking about in this particular scenario. An event, if you see here, definitions part, an event is a 5-tuple system which is P, S, S dash, M and C, where P is a process, S and S dash are the states of the process before and after the event, right? S is before the event and S dash is after the event. M is nothing but the message, and C is the channel through which the message is sent or received by P at the event, right? And also there is something called as a global state, which is denoted by SR, which consists of the states of processes of the computation and the states of the channels, right? We saw the algorithm, right? So sometime like a couple of minutes back, we read that linked predicate detection algorithm, right? So we have Chandy Lamport's algorithm over here. It's pretty simple. It's like the other algorithm. It's pretty plain English. So consider there are 2 processes. One is sending process and one is receiving process. Like I said, there are 2 rules. What does the sending process do? What is the rule for the sending process? So for each channel C incident on and directed away from P. Obviously, if you are sending something, it should be directed away from you. It should be on the other side, right? P sends one marker along C after P records its state. So P would be recording its current state and it would be sending the marker along the channel C. Now what is the receiving rule for process Q? Once receiving a marker along channel C, on receiving a marker along channel C, now Q is receiving a marker which is sent by P through the channel C. If Q has not recorded its state, so basically Q should be recording its state, right? It should record its current state. Q, if it is not recorded, obviously it's very obvious, right? It will go and record its state. Q records the state C as the empty sequence. Fine. Else, what will Q do? Q records the state of C as the sequence of messages received along C after Q's state was recorded and before Q received the marker along C. Fantastic. Let's see what the next slide talks about. So we saw what Chandy Lamport's algorithm is, and now it's a bit advancement. So using that algorithm, the author is trying to tell we can create an algorithm called as halting algorithm, which is pretty much useful for the programmer. He can use this particular algorithm and understand where exactly can he have his breakpoints. So this is also very much plain English. So there are 2 rules like process P and process Q, and if you see the marker sending rule for process P is like there's one variable which is called as halt ID, and there's a subroutine which is explained over I don't know where my cursor went. Oh yeah, I got it. Yep. So increment last halt ID, call the subroutine. For the receiving rule, on receiving the halting marker along channel C, compare halt ID with compare the current halt ID and with the last halt ID. If the halt ID is greater than the last halt ID, update the last halt ID. Else call the subroutine. What does subroutine do? It takes the process and it processes. Right? It would do some sort of function, some sort of action. For each channel C, incident on and directed away from the process X. So whichever process it is, be it Q or be it P or be it Q, send a halt marker with halt ID equal to the last halt ID along C. Along C basically means the channel that the halt ID would be sent, and halt the program. That's it. So we saw link predicate algorithm, we saw C&L algorithm, which is Chandy and Lamport algorithm, we saw halting algorithm, and so we would see what a basic algorithm in this particular scenario is, and we would see what the problems it has, and how does the author tell that he has overcome this particular thing. So basic algorithm, there are pretty much easy actually. So it's same as the the halting algorithm what we have used. Instead of halt marker, they have used marker. Halt marker instead of marker. We don't have the last halt ID. We just have the halt ID. We have something called as global halted states, which is denoted by SH. We have something called as SR, which records the states of the corresponding processes, and we have two lemmas. What are the two lemmas? Let's see that. So a lemma, I think we also had a subject called finite automata and finite languages. I think in that we have studied something about pumping lemmas, right? Whenever I see this lemma word, I just remember about that subject. So what does lemma 2.1 says? The halted state of each process in SH is global halted states, is the same as the recorded state of the processes in SR. For any lemma there should be some sort of proof, right? So the author tells that the halting algorithm is structurally identical to Chandy and Lamport algorithm. It's the same. Obviously it's a modification, that's true. In the halting algorithm, each process halts at the instant it would record its state in the C&L algorithm. Perfect. So the halted state of each process P in SH is the same as the recorded state of the process in SR. Absolutely fine. That's something very beautifully described. And pumping lemma 2, he tells the undelivered messages in each channel SH are the same as the recorded messages in the state of the corresponding channel in the SR. So basically undelivered messages are recorded in the corresponding processes is what he's trying to say. So let's see what is the problem with the basic algorithm. So like I said before, say there are two processes, one is P and one is Q. Say P to be a producer process and Q to be a consumer process, right? So there are two problems with the halting algorithm that the author has mentioned over here. The first problem is how to halt a process that has only infrequent interactions with the other processes of the computation. The process would eventually halt, that's true, potentially long after all the processes have halted. No, that's not what we are looking for, right? Even though nothing is conceptually wrong with this kind of process, it's awkward in practice. That's absolutely right? So the process would eventually halt. Who cares about the process is eventually halting or not? I want the process to halt whenever I want it, right? So if I feel that the process should halt at this particular time, it should halt, obviously, right? I'm a programmer, and if I feel that if this particular process should be halted at this time, so that I can actually understand and debug the process and then resume my program, it should be done. I can't wait till eventually it halts. That's not going to work, right? So that's one of the problem. And the second problem is one that can make both halting algorithm and Chandy and Lamport algorithm fail. Oh, that's bad actually. So this problem occurs when the network connection is acyclic. Okay, as in producer consumer or pipeline relationship, figure 3.4, with what we are seeing right now, an example of this case. Okay, so if you see 3.4 and 3.5, 3.5 is derived from 3.4, which is an extended model of 3.4. So author is trying to tell that 3.5 is a better model in order to eliminate the problem 2. If halting is initiated by the consumer process in this example, there is no way to send the halt marker to the producer process to halt the entire computation. The C&L algorithm avoids this problem by assuming the processes are strongly connected. Okay, what does our extended model tell? The extended model is an interactive distributed debugger system that works with the halting algorithm and solves the problems mentioned before. So there are two problems that we mentioned. So let's see how the extended model overcomes this. So in this extended model, there is an additional process called as process D, which is a debugger process of the system. And there are two additional control channels also connecting to the debugger process with each user process. So P is connected to D and Q is connected to D. So obviously there are two additional control channels. So P to D, D to P, P to Q, D to Q, right? The introduction of a debugger process solves not only the problem mentioned above, but it also mentioned above as in like the problems which I mentioned previously, right? It also a natural solution structure for an interactive debugging system. Now let's examine the figure instead of having much talk on this. So figure 3.5 shows the model with the user process P and Q. So here P and Q is the user process and D is the debugger process. Since each process has two control channels, one from debugger process, and the network is strongly connected, obviously, that we assumed previously also, right? There's always a message path from process to any other process. Yes, that's true. In addition to guaranteeing strong connectivity of the network, the debugger process performs the typical functions of a debugger. This is what we wanted, right? So the basic idea of any halting algorithm or any breakpoint is to debug the particular process or a program, right? So we are actually getting closer, right? It's a good solution. It's a pretty much straightforward, simple solution, but that it's actually satisfying the purpose what we are actually looking for. The algorithm to halt the computation need not be changed except that the process are always willing to accept a message from the I'm sorry, I missed that. So the algorithm to halt the computation need not be changed except that the debugger process D never really halts. Okay. Here the author is telling that it's ensured that the user process are always willing to accept a message from the debugger process by making the arrival of a message from the debugger process asynchronously interrupt as the user process. Obviously, if debugger is sending some process to the user process, it's priority based, right? So not priority based, it's a prioritized request. Yeah. So obviously, user process has to or have to accept that. Yeah. So I think it's a pretty much simple solution that the author has implemented over here. He just introduced the debugger process, which solves the above two problems or the problems that we spoke some time back. That's it. That's pretty much about the extended model. We would see what are the applications to current research. So there are two approaches that's been followed. The first approach avoids the problem of stopping a program by providing tools only for monitoring a program's execution, right? So it's just for monitoring a program's execution is what you're seeing here. And the second approach to distributed debugging is one that more closely approximates traditional single process debuggers. So this is what the current research is, the applications to current researches are. And like I promised, I would be concluding this particular presentation. So we saw what interactive debugging is, right? So we saw what interactive debugging is. We saw different types of predicates, all those things. So let's quickly try and understand and finish the presentation. Interactive debugging is a familiar scenario to any programmer. Any programmer, wake him at around 2 a.m. and if you ask him about interactive debugger system, he should be able to explain you. And he would be the one who would be the most happiest person to talk about interactive debugging, because if he has had any experience in interactive debugging, and he would have loved that particular experience. The definition of distributed breakpoints presented previously and the halting algorithm which was presented previously provide the programmer with the necessary tools to apply these techniques to a distributed program. The fundamental idea is that the program's view of event ordering and relative timing is preserved. That's absolutely true. Going through this particular article, this is 100%. I can go with the author. Any software debugging tool will cause some change in the absolute timing of a program. That's there, right? There would be some sort of delay. There would be some sort of timing changes in this with respective softwares. So what the author is trying to say is they have not tried to avoid this. It's impossible to avoid this. Be it at any point, be it 20 years after now on, this would be there. So he's telling that he's not tried to avoid this, but the algorithms what they have implemented only impose a minimal change of the execution of a program. Now this change is the one that should not affect any but the most time sensitive programs. That's true. And for these programs, a hardware monitor may be the only suitable form of debugger. Absolutely true. Having a hardware monitor would actually act as an added advantage, is what I can tell. That's it. That's pretty much it. I hope you would have understood what the presentation was about. Hopefully you enjoyed it, and so if you see the references, so these are the two references. I actually browsed through the net, and these are the two references that gave me some sort of idea of all these things that we spoke about. So quickly glancing, I think we spoke about the abstract. I gave about a brief introduction about what are the things that we are going to speak. We saw what are distributed breakpoints. We saw consistent halting. We saw application to current research. Conclusion, right? Question and answers in a presentation on YouTube. that's funny, right? So basically, this presentation was to be presented in the class, and since our beloved lecturer did not find sufficient time to sit and listen in the class, so this is the idea that a professor brought into picture, that you can actually go and record your seminars on a screen capture, and then upload it on YouTube. Just give me the link, and then I would be watching your seminars. That's a very good idea, right? Yeah, that's it. And last but not the least, I would like to say thank you for watching the presentation end to end. Love you guys. Take care. Thank you. Bye bye.